Now, naturally, before we talk about equilibrium, which is a part of your syllabus in class 11, or rather, before we talk about reversibility, we'll need to go past the tenets of the dynamics of a reaction in one direction first, then we can talk about reversibility. And naturally, we'll begin with something called rate of reaction, rate of chemical reaction. I might have told you in the past, in general, a chemical reaction would be a set of reactants becoming a set of products. And naturally, by rate of reaction, I would either mean the rate at which reactants disappear or the rate at which products are appearing, or the rate of formation of products. So it's either the rate at which reactants decrease or the rate at which products increase, which I'm again going to refer as a delta R delta T or a delta P delta T, where for delta P delta T, I would put a positive sign, and for delta R delta T, I'll put a negative sign. Yes, you understand, delta will always mean a change, delta will always mean a change. So when I talk about delta R delta T, when I talk about delta R delta T, I put a negative sign here because naturally, for R2 minus R1, I'll assume it's negative because R2 will be less than R1. Naturally, R2 is the amount left after time T2. R1 is the amount left after time T1. Naturally, T2 is later than T1. Reactants will decrease with time. So you'll want to keep a negative sign before the reactants and positive sign before the products. A very classical example, or a very simple example of how we go about equating the rate of different reactants and products is, and maybe I'll want to use this part of the board. I hope you have copied it so far. So many times you'll not need to copy because I've given you a basic introduction of this in the video classes. You will just want to respond with a yes or no and we'll want to move on. But chalo, hana bolo.
Yes, sir.
So a very popular reversible reaction, and I'll talk about reversibility a little later. Naturally, I'm talking about the process happening in one direction. And nitrogen gaseous, hydrogen gaseous, forming ammonia, the very famous Haber's process. Haber got a Nobel Prize in chemistry for this process because, this led to enormous increase in the amount of food on the planet. Without ammonia, you could not have prepared any fertilizer, and without fertilizer, the land would not have yielded enough food for the population to grow the way it has grown. So, very philosophically, I might end up saying so many of us owe our lives to Haber's process. You had a lot of nitrogen in the air. It's the principal component of atmosphere. Almost 80% of the air is nitrogen. But converting nitrogen to hydrogen forming ammonia, which looks like a very common equation now, was the outcome of decades and decades of research. Haber's process, scientist Haber came up with a method of preparing ammonia. We'll talk about the reversibility when the time is right. But 1 mole of nitrogen with 3 moles of hydrogen producing 2 moles of ammonia. 1 mole of nitrogen with 3 moles of hydrogen producing 2 moles of ammonia. And for gases, mole ratio is the same as volume ratio. So 1 mole of nitrogen reacting with 3 moles of hydrogen producing 2 moles of ammonia. I keep on saying is as good as 1 liter nitrogen reacting with 3 liter hydrogen producing 2 liters of ammonia. And by the time nitrogen decreases by 1 liter, hydrogen would have decreased by 3 liters. So allow me to say that when it comes to del N2 del T, it's basically 1/3 of del H2 del T. In other words, del H2 del T is 3 times del N2 del T. Yes or no? And naturally, the rate of formation of ammonia this would be 2 times of del N to del T, or in other words, del N to del T is half of del NH3 del T. The rate of disappearance of nitrogen would be half of the rate of appearance or formation of ammonia. And this is how we end up equating the rate of a chemical reaction in terms of the rate of appearance or disappearance of different reactants and products. So many times you might have a very simple question like, one of the values are given, and from the balanced equation using the stoichiometric coefficient, you will want to find the rate of change of the other components. So in a given problem, in a given problem, if del N to del T, if del N to del T is suppose 0.5 moles per liter per second, you would want to believe that del H to del T is certainly 3 times of this, which is 1.5 moles per liter per second, and del NH3 del T is 2 times of this, which is 1 mole per liter per second. I think you all are happy with this. बच्चे लोग हाँ ना बोलो. Let me add a basic information to what otherwise looks like balancing chemical equation and some stoichiometric coefficient being able to derive the rate of change of different reactants or products, with respect to each other. Let me quickly add, certainly in a general reaction when reactants and products would change at different rates, by general rate of the process, I'll always mean the rate of the slowest mover. So this is the slowest mover here. Del to del T, del H to del T, del ammonia del T would be different. So what would be the general rate of this reaction? The general rate of this reaction would be the rate at which nitrogen is changing. बच्चे लोग हाँ ना बोलो. So by rate of the process, I would go by the rate of the slowest mover, which is say nitrogen in this case. Hello. Good afternoon. खबर बढ़िया है, क्लास में है, फोन करते इत्मीनान से. In general, if you have a reaction like A moles of A with B moles of B producing C moles of C and D moles of D, where you understand small a, b, c, d are numbers used to balance the equation. Capital A, B, C, D are different reactants and products. And again, I would have briefed you about this. How you go about equating them is, we'll want to naturally put a negative here. Every time I talk in terms of the rate of change of reactants, I'll want to put a negative before the reactants. I think I'm being understood here. But chalo, हाँ ना बोलो. You put this stoichiometric coefficient in the denominator. You had an example of this kind, and this is how you can equate the rate of change of different reactants and products. I think you all are understanding me. This is how you will summarize the result in general, a general equation of this kind, and this is how you will be able to equate the rate of change of different reactants and products. Fair enough? After this, we talk about the very fundamental basic principle or the law of mass action, the first rule which spoke about factors affecting rate of chemical changes. Next heading should be law of mass action. Given by two scientists, it will help if you tell me the name of those two scientists. You would have. Yes, please. Yes, two people, Goldberg and Vogge. WBJ में एक बार ना ये नाम भी पूछा था, और मैं ईयर भी लिखा देता हूँ. 18. ये एक बार चेक कर लेना. मैं हर साल बहुत कॉन्फिडेंटली ये लिखवा देता हूँ, मैं कभी क्रॉस चेक नहीं किया हूँ. So it all began with the fundamental law, which is called law of mass action. Allow me to remove this clutter. Now, law of mass action, which I told you, is say the most primitive and the first rule about rate of processes given by these two scientists. Know the name and just cross check the year 1864. And it states that the rate of the process, the rate of the reaction would be proportional to the active mass of reactants. Active mass of reactants. Now, temperature remaining constant because we see temperature have a different effect altogether. So temperature remaining constant. This, in principle, is law of mass action. It states the rate of a process is proportional to the active mass of the reactants. I repeat again, active mass might be an old term, a primitive term. Now, by active mass, I'll assume its concentration, and the most popular unit of concentration is molarity. Now we want to deal with everything in terms of moles per liter. And it's simple as it sounds. If you have A moles of A with B moles of B becoming products, law of mass action tells you that this rate is proportional to concentration of A to the power alpha, concentration of B to the power beta. You'll want to bring a proportionality constant, which is very popularly called rate constant. And to begin with, this is going to be the very popular rate law expression. Physical chemistry, organic chemistry, everywhere, I would be using it. Sir, alpha beta is smallest one. Sorry? Alpha beta does have stoichiometric correlation. This alpha is expected to be A, this beta is expected to be B, and if alpha is equal to A and beta is equal to B, or if alpha plus beta is equal to A plus B, if alpha plus beta is equal to A plus B, you call it an elementary process. See, alpha is the order with respect to A. Alpha is supposed to be the order with respect to A. Beta is supposed to be the order with respect to B. Alpha plus beta, which supposes the number n, and you call it the nth order reaction. And trust me, all of this order is always calculated experimentally. It's always found experimentally. It's always found experimentally. In case you have not noted it in the past, you'll want to write it here. I'll very quickly explain a few things. Because law of mass action, I told you, is the first fundamental principal rule. It's as simple as A बढ़ाओगे, B बढ़ाओगे तो रेट बढ़ेगा. A बढ़ाओगे, B बढ़ाओगे, रेट बढ़ेगा. It's based upon, again, the fundamental principle of collision of particles. So particles collide, the reactant particles collide, and all the effective collisions they mature to product. This is the principal rule in chemistry. This is supposed to be happening almost every time. Reactant molecules collide, and all the effective collisions mature to product. So if you increase reactants, naturally the number of collisions and the chances of formation of product would increase. It's like if you put more fuel, the fire will be more vigorous. Yes or no? A बढ़ाने से रेट बढ़ेगा, B बढ़ाने से रेट बढ़ेगा. Keep in mind, we are not talking about a temperature change. Very soon you will understand temperature will change the value of K. So right now I don't want to play around with K. I want to play around only with the concentration part. K rate constant will be a function of temperature only. K rate constant will be a function of temperature only. K is called rate constant. K is called rate constant. From now on, anything which is there in square bracket would be in molarity. So this is the amount of A or B at any instant of time, and the corresponding R could be obtained in this way. It will have immense application in all forms of chemistry, I told you. But again, to take a few things forward, K is called rate constant. or velocity constant or specific reaction rate. People online would want to respond. I think this was all there in the introduction which I gave you. You just
Yes,
want
sir.
to respond with a yes or no. And by now, you know, this is a function of temperature. This depends on temperature only. This depends on temperature only. So at a given temperature, when the value of K is constant, the rate will be a function of the amount of A or B. Alpha is the order with respect to A. इमेजिन अगर अल्फा वन होता है, तो ए को डबल करने से रेट डबल हो जाएगा, ए को ट्रिपल करने से रेट ट्रिपल हो जाएगा. बट अगर अल्फा टू होता है, इफ इट्स प्रोपोर्शनल टू ए एंड स्क्वायर ऑफ इट, तो ए को डबल करने से रेट 4 टाइम्स हो जाएगा. यस और नो? ए को ट्रिपल करने से रेट 9 टाइम्स हो जाएगा. अल्फा वन है तो हम लोग इसको फर्स्ट ऑर्डर रिएक्शन बोलेंगे, अल्फा टू है तो सेकंड ऑर्डर रिएक्शन बोलेंगे. अल्फा थ्री भी हो सकता है. अगर अल्फा का वैल्यू 3 है तो r इज इक्वल टू a टू द पावर 3, एंड a को 3a कर देंगे, a को 2a कर देंगे टू द पावर 3, देन r विल बिकम 8r. यस और नो? a बढ़ाने से r बढ़ेगा, a बढ़ाने से r बढ़ेगा. अल्फा विल टेल यू किस ऑर्डर में बढ़ेगा, अल्फा विल टेल यू किस ऑर्डर में बढ़ेगा. Again, a little bit more about K. Every time you have something in the form of specific heat, resistance, conductance, you learn in 12. Specific heat, 1 gram, 1 degree Celsius amount of heat required. Specific resistance, you know, the resistance of a unit cube. तो जहां पर भी ये specific term use करते हैं ना, you can define it in this manner. So K could be defined as the rate. K could be defined as the rate if the concentration of the reactants is 1 molar each. Yes or no? How do you define rate constant? You can define rate constant as the rate of a process for unimolar concentration of the reactants. I hope you all are understanding me. बच्चे लोग हाँ ना बोलो.
Yes, sir.
It's a function of temperature only. It's a function of temperature only. A lot of things, you know, would become very, very obvious in due course. A lot of things will become very, very obvious in due course, but a few things that you want to know about the rate law expression, like A and B, which are these stoichiometric coefficients, if these two are added, it's called the molecularity of the reaction. And I've already told you that alpha and beta is called the order of the reaction. And then only if MR is equal to OR, if order is the same as the molecularity of the reaction, you will call it an elementary process. This will happen many times. In general, this is what we'll do in problem solving. But this may or may not be true. Because A and B, you know, are going to be numbers which will be used to balance the equation. Whereas alpha and beta, I told you, is always obtained experimentally. Alpha and beta is always obtained experimentally. I think you will start understanding about the role of alpha and beta. नाम ऑर्डर से समझ में आता है. मैं एक बार वापस बताता हूं. प्लीज हियर मी आउट. I don't want to prove it mathematically right now. If you hear me out, you will understand it right away. If alpha is 1, you change A 2 times, rate would change 2 times. You change A 3 times, rate would change 3 times. So basically, if alpha is 1, you call it a first order with respect to A. And if alpha is equal to 2, you change A 2 times and rate would become 4 times. Yes or no? Same for beta in terms of the concentration of B. So alpha and beta will decide by what order the rate will change. A and B are going to be numbers used to balance the equation. Alpha and beta are always found experimentally. Now order may be zero, negative, or fractional. Order may be zero, negative, or fractional. Order may be zero, negative, or fractional. We'll talk about zero order, we'll talk about negative, we'll talk about fractional. But A and B are going to be integers only. So naturally, there will be so many instances where order and molecularity will be different. In case they are equal, which is the case more often than not, we will call it an elementary process. And naturally, if MR is not equal to OR, if MR is not equal to OR, we'll learn more about it. We'll want to call it a pseudo order reaction. We'll want to call it a pseudo order reaction. I told you we'll learn about each and every aspect in details. You'll want to take a note of a few things right now. Order might be zero, negative, or fractional. So naturally, order and molecularity may differ so many times. Molecularity is by balancing the equation. Order is always obtained experimentally. It could be negative or fractional, zero, and naturally, I would have told you in the past, order more than 3 is very unlikely. Order more than 3 is very unlikely or not possible because the probability of more than 3 particles colliding together, more than 3 particles colliding together is very, very rare. We believe in a three-dimensional space. We believe in a three-dimensional space. And trust me, this would help you in solving problem right away. Everything which I tell you in theory is keeping the questions in mind. So these are facts you'll want to know. Order could be zero, negative, or fractional. Order more than 3 is not possible because that would call for more than 3 particles colliding together in the same step. You will relate with it right away when I talk about reaction mechanism in organic chemistry. Maybe down the line, a couple of weeks later, I talk about SN1, SN2, just in case you have read a bit of it. You see SN2 order 2 would mean 2 particles are colliding together. Order 3 might require 3 particles colliding together. So order more than 3 is very unlikely because more than 3 particles colliding together is pretty unlikely. For the time being, these are facts which you'll want to know about order, molecularity, rate law expression, rate constant, and we'll want to move on. बच्चे लोग हाँ ना बोलो. You're all happy with this?
Yes, sir.
I would have wanted to add, a few more layers of information to rate constant in terms of temperature, but maybe I'll want to do it a little later. I would quickly, revise things which I gave you in the introductory video. So allow me to remove this clutter and let's go back to the elementary form, which is rate proportional to the amount of reactants. Again, when it comes to catalyst, when it comes to temperature, it's going to be a different approach altogether. I'll maybe tell you about all of that at the next opportunity. Allow me to remove this clutter. Can I rub it off? बच्चे लोग हाँ ना बोलो. Did you turn on the light right now? It will have a reflection on the board. That's the reason I keep it off. We can carry on. Now, people online will keep on responding. Rate is equal to K reactants to the power N for an nth order reaction. I can tell you a few things like the unit of K, unit of K. I don't know if I give you this in the video or not. But if the rate is moles per liter per second, if the rate is moles per liter per second, and the concentration is moles per liter to the power n, the unit of K would be moles per liter to the power 1 minus n per second. So again, a piece of information which will be handy in solving questions right now. The reactants will decrease with time. The reactants will decrease with time. So naturally, the rate of a process would decrease with time. Now we know that all reactions are reversible. Now we know that all reactions are reversible. So what I was writing as A moles of A and B moles of B producing C moles of C and D moles of D, I start using a reversible sign. And in the beginning of reversibility, I tell you a story which is about Na2CO3 and CaCl2 forming NaCl and calcium carbonate. It's actually printed in a few textbooks. I don't know whether it's there in the current textbooks you are having access to or not. But it's supposed to be a historical fact. It's supposed to be a historical fact. Initially, people believed reactions happen in one direction. Initially, chemists believed reactants become products because products are more stable. Yes or no? There is no doubt about the stability of NaCl, which is the common salt. And you know, all the oceans and sea bodies are filled with, marine waters are filled with NaCl. Similarly, calcium carbonate, limestone, dolomite, chalk, marble, different forms of calcium carbonate, NaCl and CaCO3 both are abundant in nature. Something abundant in nature would always speak of its stability. So we always believe sodium carbonate would react with calcium chloride, forming sodium chloride and calcium carbonate. And I narrate you this story. I think it was there in the video class. It was about a lot of sodium carbonate, which in the native language was called trona, which was found in the marine waters or marine lakes of Egypt. So yet again, God knows whether it's a fact or a tale. But when they discovered a lot of sodium carbonate, at some point of time, sodium carbonate is very soluble. All sodium salts are soluble. And where, and if you are wondering how did the sodium carbonate accumulate along the banks of, the marine lakes and marine water bodies, they found there's a lot of NaCl in water because it's salty, and the river bed or the bed of the water body, it contained a lot of calcium carbonate. And historically, this is supposed to be the first instance where people believe that product might also react back to give reactants. I repeat, this is more of a very prominently narrated historical fact. The sodium carbonate, and people started thinking that this reaction can happen in the reverse direction as well. And this set the ball rolling. Now we know all reactions are reversible. Now we know all reactions are reversible. Now we know all reactions are reversible. Now we know all reactions are reversible, provided there is no sink. Did I speak about sink in the class?
Yes, sir.
Sink is something which is irrecoverable. Sink is something which will precipitate, leave the system, or would, uh, go out as a gaseous emanation. So naturally, you have questions like a piece of paper when burned, it burns completely. When a piece of paper is burned, or suppose this compound calcium carbonate is thermally heated, thermal decomposition, burning, thermal decomposition, burning, and you can't cite reversibility there. Naturally, because when there is a state of matter leaving the system, you also end up calling it heterogeneous equilibrium, which is difficult to set up if the system is not closed because carbon dioxide would go out. So all of calcium carbonate on heating and all of it will get decomposed. But I also add that carbon dioxide turning the lime water milky is if possibly carbon dioxide is put into calcium oxide or calcium hydroxide, it will produce calcium carbonate as well. Yes or no? So even in cases where there is a sink and they look irreversible, the reverse reaction could be carried out. All of the paper gets burnt down. All of the hydrocarbon will be burnt because from a solid or liquid form, a hydrocarbon or a piece of paper would burn producing carbon dioxide, water, which in vapor form or liquid form, would be in a different state of matter, in a different state of matter. Largely, we are going to deal with, gaseous state. And if all of them are in the same state of matter, if it's a closed system, trust me, a reaction will never get over. A reaction will never get over. When I say a reaction will never get over, no reaction is 100%, no reaction is 100% completed, no reaction is 100% completed. And now, I'm talking in lines of reversibility. No reaction is 100% over. It means you will have both reactants and products always present in a closed reaction vessel. So if it's a closed system where you're performing a reaction, no matter how hard you try, under optimum conditions using the best possible catalyst, you'll not be able to convert 100% of reactant to product. Reactant and product would be coexisting. Reactant and product would be coexisting. And now I believe, all reactions are reversible. All reactions are reversible. A very nice example I would have given you in the introductory video is I talk about this reversibility where NO2 dimerizes to N2O4 and N2O4 is colorless and NO2 is dark brown. Naturally, because NO2 is paramagnetic, has unpaired electron, N2O4 would be colorless. And if you remember the story, I would want you to take pure NO2. I would want you to take pure NO2 and pure N2O4. The moment you see pure NO2, it would start dimerizing. So right away you see pure NO2, which is very dark, losing its color because in course of dimerization, it will start losing its color. And almost colorless N2O4 would start picking up some color because of this reaction happening backwards as well. And I also tell you that if you happen to bring both of them in a common water bath, if you bring both of them next to each other, a common water bath means you're taking them into identical conditions. And you'll find in due course both of them will have same color. They'll have same color. So if they have same color, which is why naturally the system of NO2 losing its color, fading away, and pure N2O4 picking up color is about NO2 moving forward and N2O4 moving backward. And same color would mean at some point of time they'll have the same concentration of both the reactant and products. Reactants is more the process moves forward and the product is more the process moving back. Naturally. Another good example is hydrogen and I mean, every reaction which you learn in this topic would be reversibility. We choose something like this because this is colored. You're getting me? Although iodine is also colored, to be fair. And all the cases we'll take up would be about reversibility. All reactions are reversible provided there is no saying. What I conclude here is this reversibility or this state of what we are going to call as a state of equilibrium can be arrived both from the reactant as well as products. So once I've told you a little bit about reversibility, I would want to go back to the law of mass action to prove it. I think people online are hearing me out. We'll want to go
Yes.
back to law of mass action, and now we'll talk about reactions forward as well as backward. I talk about reactions forward as well as backward. Which is say for AA plus BB becoming CC plus BD, and I believe that all are elementary processes, order and molecularity is same. I would write RF is equal to KF A to the power A B to the power B. I mean, we are going to be more used to alpha and A being equal, beta and B being equal. So we'll begin with the likeliness of a process being elementary only. Also, I've already told you the difference. It's not like it will be the case every time. And what I write to the left is generally a set of chemicals I begin with. The reactants are the set of chemicals I begin with. So at time t is equal to 0, I believe I have maximum of A and B, and rate forward will be maximum. The rate forward will be maximum. I gave you a plot of this kind where I plot the rate of the process with the progress of the reaction or time. And generally, this is supposed to be the plot of a forward reaction, which you see is decreasing with time. Now, no doubt about a process and its rate falling with time because reactants will react. Reactant का amount कम होगा. Reactant का amount कम होगा तो rate forward कम होगा. And with time, C and D will build up. Initially, if C and D are not there at all, it might begin from the origin and it's gradually building up to a point where, say, RF and RB are equal. When RF and RB are equal. Now, this is called the point of equilibrium. This is called the point of this time, and you'll call it the point of equilibrium. All right. We're doing SSM right now. So there is again, a state of equilibrium, but although the two are very different and should not be related. A similarity would be if there are no other forces disturbing the system, even that would keep on happening forever. Yes or no? Yes or no? Here again, you believe the process has come to a standstill. In chemistry, you believe the process has come to a standstill. How do you realize that a process is over? There is no change in temperature, color, density. कोई साउंड नहीं आ रहा है, कोई आवाज नहीं आ रहा है, कोई टेम्परेचर चेंज नहीं हो रहा है, प्रेशर रीडिंग टेम्परेचर रीडिंग कांस्टेंट हो गया, तुम बोलते हो रिएक्शन रुक गया, पर रिएक्शन कभी रुकता नहीं है. मतलब इक्विलिब्रियम आ जाता है which I am going to call as a state of dynamic equilibrium. और यहाँ पर RF is equal to RB. I hope this is not difficult to understand. Initially at time t is equal to 0, you'll have maximum RF because you begin with a set of reactants. A and B will be maximum, so RF will be maximum to begin with. With time AB कमेगा, rate कमेगा. With time C और D बढ़ेगा तो RB बढ़ेगा. जब RF और RB बराबर हो जाएगा, it's happening forward and backward at the same rate. So there is no net change. And when I say there is no net change, certainly the amount of A, B, C, and D, KB is a constant, Kf is a constant, and you start calling it Kc, which is the equilibrium constant, which is the equilibrium constant. Rate constant is a constant, it depends only on temperature. So Kf, Kb is constant, Kc is also a constant, and this would be C to the power C, D to the power D, upon E to the power A, B to the power B. And like Kf, Kb were functions of temperature, like Kf, Kb were functions of temperature, Kc would also be a function of temperature. Like Kf, Kb depend only on temperature, Kc would depend only on temperature. At equilibrium, the amount of A, B, C, and D will be constant with time. And this is where I tell you, apparently there is no change in the amount of reactant and product. You feel the process has stopped, but it never stops. It keeps on happening in the forward and backward direction at the same rate. And the state of equilibrium is dynamic. बच्चे लोग खाना बोलो. एक पॉइंट पे मैं तुमको टुवर्ड्स द एंड ऑफ आयोनिक इक्विलिब्रियम पढ़ाऊंगा कि जब कोई सॉलिड प्रेसिपिटेट भी कर जाता है ना, सैचुरेटेड सॉल्यूशन में अगर प्रेसिपिटेट कर जाता है, द प्रेजेंस ऑफ अ प्रेसिपिटेट वुड प्रूव दैट द सॉल्यूशन इज सैचुरेटेड, वरना वो प्रेसिपिटेट ही क्यों रहता. वहां पर भी इट कीप्स ऑन प्रेसिपिटेटिंग एंड डिसॉल्विंग एट द सेम रेट. That should be a topic called solubility product, which we'll be doing much later towards the end of ionic equilibrium. So even if a precipitate is found sitting idle in the system, which so many times is believed to be out of the equilibrium because it's precipitated, might also involve an equilibrium, but it keeps on dissolving and precipitating at the same rate. In this case, a process which is otherwise appearing to be, stopped is happening both forward and backward in the same rate. I think you have got an idea about Kc equilibrium constant now. I think you've got an idea about Kc equilibrium constant now. बच्चे लोग हाँ ना बोलो. Now, if you tell me, I can suddenly, take you to a different path altogether where I can talk about temperature and catalyst in today's class itself. I mean, I'm looking to take the class till 4 p.m. So in that amount of time, I think I'll be able to go past a lot of, information regarding temperature and catalyst. Let's do that right now. Let's take this opportunity to do it right now, because volume, pressure, AC, KP is something which I've introduced a little bit. You'll want to, come a little more prepared with that next day. I'll do that again. I'll do that when I'm doing pressure, volume, and all. All right. But because we have some time left right now, I would want to do something which is far more conceptual. All right. So because I have told you a little bit about Kf, Kb, Kc, equilibrium constant will be a constant, and a value of Kc higher would mean it's more forward, it's more feasible in the forward direction. See what we are up to. Everything which we learn in this topic will find real life application. So when you are preparing ammonia in a plant, naturally ammonia में fertilizers का भी property है, बॉम्ब बनाने का भी प्रॉपर्टी. हेबर को जब नोबेल प्राइज मिला था, half the science fraternity did not attend, that grand event of Heber getting the Nobel Prize. Some people were also willing to, return their Nobel. Yes. Yes. World War II के टाइम में तो अमोनिया से खाना बनाया. People started saying he is making bread out of air. And then ammonia got application into ammonium nitrate, which was an explosive. Ammonium nitrate, TNT, amatol, chlorine banaya, which killed thousands of people in the Allied Army. He was a man of science. Maybe, he was serving his nation in a world war, but you could make a hero and a villain out of the same person. ये सब मैं क्यों बताने लग गया अभी. अमोनिया अगर बनाते हो फर्टिलाइजर्स के लिए या बॉम्ब बनाने के लिए, you will want to know factors which will increase the content of ammonia. Every process is reversible, but everything which we learn right now would eventually contribute to what's happening in real life. You would want to know about factors which will increase the amount of product You can't help reversibility. But certainly, if the value of Kc is higher, it's more forward in the it's more visible in the forward direction. Yes or no? हाँ, products निकालते जाओ. That will be one method of keeping the equilibrium forward. एक्सोथर्मिक में टेम्परेचर घटाते हैं, एंडोथर्मिक में टेम्परेचर बढ़ाते हैं. उल्टा बोल रहे हैं भाई, उल्टा बोलेगा तो सब उल्टा हो जाएगा. क्या बोलते हो बोलो? कुछ नया अच्छा तो चीज अभी फटाफट पढ़ा दूं 1-1.5 घंटे के अंदर में कि भाई केसी केपी अल्फा पी वी वही सब कराता हूं. Come on, quickly tell me. Can have a quick round of poll here. People online, offline, tell me quickly. People offline, they have gone quiet for some reason. So you will want to be all ears. You want to be all ears. I'm talking of something which is very, very conceptual and would account for questions in different branches of science. I told you K is a function of temperature. I told you K is a function of temperature. This is the very popular Arrhenious equation. This is the very popular Arrhenious equation which tells you how K changes with temperature. This is the raw crude form. E exponential वाला E है. E exponential वाला E है. ठीक है. A को बोलते हैं प्री एक्सपोनेंशियल फैक्टर. A को बोलते हैं प्री एक्सपोनेंशियल फैक्टर. इसका एक और नाम है फ्रीक्वेंसी फैक्टर. Now everybody would want to start writing because this is not there in the introductory video. Pre-exponential factor or frequency factor is a constant for many reactions of the same type. It will be a big value. It will be a big value, and it would be constant for so many reactions of the same type. You know, E is exponential. इसको pre-exponential भी बोलते हैं. E is a number. E is called activation energy. कौन बोल रहा है activation energy भी? कौन बोला activation energy? R is universal gas constant. R is universal gas constant. PV is equal to nRT वाला. And T is temperature in Kelvin scale. This is temperature in Kelvin scale, capital T. So if you understand me, A is a constant, E is a number, activation energy will be a constant for a given reaction, R is a constant. The only variables are T and K. The only variables are T and K. The only variables are T and K. So I told you Arrhenious equation is about how K changes with temperature. I told you rate constant is a function of temperature. This is the crude raw equation, which is called Arrhenious equation. To simplify it or to make it a more application oriented, we'll want to take log on both sides. You know, ln k would mean I'm taking natural logarithm. So you understand log of a to the power x to the base a would be x only? Yes or no? I hope you're understanding me. Log of AB is log A plus log B, and naturally log to the base E minus EA by RT would be the same as EA by RT. Yes, you also know when you have to convert natural logarithm to common logarithm, there is a multiplication factor of 2.303. And I'll end up getting an equation like log K is equal to log A minus E upon 2.303 RT. See what I'm up to? I'm taking 2.303 common. You understand? I'm converting natural logarithm to common logarithm, and I'm taking 2.303 common and dumping it in the denominator out here. Now let me call it the logarithmic form of. Let me call it the logarithmic form of Arrhenious equation. The crude form was k is equal to a into e to the power minus ea by rt. I think you are understanding the journey of converting the the Arrhenious equation to the logarithmic form. I hope you're understanding me. This will be easier to work with. This will be easier to work with. I've given you the Arrhenious equation, and then the logarithmic form of Arrhenious equation, which I told you, will be more application oriented. क्या मैं 2.0 कॉमन लिया हूँ और ये अपॉन 2.03 आती बना दी है ना. ऑल राइट. Now I'll start with the logarithmic form. It's going to look like the equation of a straight line. So one very common question is from log k is equal to log a minus e upon 2.03 or log k is equal to log a minus e upon rt. There could be a graph where you're plotting log k versus 1 by t, and it will be like y is equal to mx plus c with a constant slope, and the slope will be negative. Yes or no? This value would be log a, and the slope would be minus ea by r, or minus 2.303 minus e upon 2.303 r. Now this will be minus 2.303 by r. If naturally it's plotting against yes or no? बच्चे लोग हाँ ना बोलो. तो कभी कभी ऐसे ग्राफ दे देता है. This looks like the equation is y is equal to mx plus c. You know the y ordinate would be log a, and the slope would be minus ea by r. The slope would be minus ea by r, negative slope, or minus ea by 2.303 r, depending whether you're using natural logarithm or common logarithm. This is one type of question which is there in the exam. I felt like sharing it, but we'll want to talk about the logarithmic form now. Do you all relate to what I'm up to? बच्चे लोग हाँ ना बोलो. Do you all relate to what I'm up to? क्या कर रहा हूँ बताओ. चलो, I would have wanted some, intellectual answers from you. You think this is the time? What I'm up to?
Constant eliminate.
I'm getting two different values of k at two different temperatures. I told you it was about k changing with temperature. I told you k is a function of temperature only. टेम्परेचर T1 पे अगर वैल्यू K1 है तो टेम्परेचर T2 पे वैल्यू K2 होगा. टेम्परेचर T1 पे वैल्यू K1 है तो टेम्परेचर T2 पे वैल्यू K2 होगा. I'll call it equation 1, I'll call it equation 2, and 2 minus 1, log A minus log B will be log A by B, log K2 by K1. Naturally, log A will get cancelled. It will be 2.303 R, EA 2.303 R common, 1 by T1 minus 1 by T2. Realize because I'm taking 2 minus 1, I'm taking 2 minus 1, the one involving T1 would become positive. And this is going to be such an important equation. This is going to be such an important equation. You'll have questions directly coming from this. You'll have questions directly coming from this. बोल बेटा बोलो ना बच्चों मैं लेता आऊंगा ठीक है बेटा बाय Now, temperature in Kelvin scale, temperature in Kelvin scale would mean it can never be negative. Temperature in Kelvin scale, if T2 is more than T1, if T2 is more than T1, K12 is more than K1. बच्चे लोग हाँ ना बोलो टेम्परेचर बढ़ाने से K बढ़ता है टेम्परेचर बढ़ाने से K फिर कोई जवाब ही नहीं दे रहा है टेम्परेचर बढ़ाने से K बढ़ता है टेम्परेचर बढ़ाने से K बढ़ता है K बढ़ेगा तो रेट बढ़ेगा K बढ़ेगा तो रेट बढ़ेगा initially you were bothered about order rate flow expression you keeping temperature constant. Now if the temperature is changing and R is equal to K reactant to the power N, so now how would the temperature affect the process? Log R2 by R1 would be log K2 by K1, which would be EA T2 minus T1 upon 2.303 or T1 T2, yes or no? Yes or no? So you believe K बढ़ेगा तो रेट बढ़ेगा टेम्परेचर बढ़ाने से रेट बढ़ता है 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 दिस इक्वेशन टेल्स यू एग्जैक्टली कैसे बढ़ता है if you know the activation energy then you can relate the value of K and rate at two different temperatures yes or no सिर्फ ये याद रखना कि E और R को सेम यूनिट में लिखना EA और R को सेम यूनिट में लिखना कभी कभी क्या होता है EA को जूल्स में दे देता है R को कैलोरीज में दे देता है अगर ये जूल में है तो इसको 8.314 लिखना ये कैलोरी में तो इसको 2 लिखना put E and R in the same unit that's a common mistake but simple as it looks T2 more than T1 टेम्परेचर बढ़ाने से T2 more than T1 टेम्परेचर बढ़ाने से रेट कांस्टेंट बढ़ेगा रेट बढ़ेगा रेट कांस्टेंट बढ़ेगा रेट बढ़ेगा only to give you a little more information मैं बताऊंगा let me give you one more term which is called temperature coefficient let me give you more term which is called temperature coefficient is supposed to be the ratio of the rate of a process with every 10 degrees Celsius or Kelvin change in temperature. So when I write RT plus 10 by RT, it's the ratio by which the rate is changing per 10 degrees Celsius or Kelvin increase in temperature. Yes or no? Ideally, it's R308 by 298. You would have known 298 Kelvin or 25 degrees Celsius is supposed to be the standard temperature. 25 degrees Celsius is supposed to be the normal temperature, the average temperature. 25 degrees Celsius is supposed to be the average temperature of maximum laboratories of this planet. So it could be between any T and T plus 10. And I think I've defined temperature coefficients for you. Temperature coefficient is the ratio of the change of rate or the rate constant per 10 degrees Celsius or Kelvin, change in temperature. ये तो थोड़ा थोड़ा क्वेश्चन में आता है. It generally lies between the value of temperature generally lies between 2 to 3. It generally lies between 2 to 3. Again, these are facts. These are theoretical facts. Would help you in solving some questions. You'll want to keep a note of it. I think you're all understanding me. बच्चे लोग हाँ ना बोलो. So far so good. कोई मेरे से पूछ रहा है एक्टिवेशन एनर्जी क्या होता है. मैं डेफिनेटली बताऊंगा एक्टिवेशन एनर्जी क्या होता है. पर किसी भी रिएक्शन का एक्टिवेशन एनर्जी कांस्टेंट होता है. आर कांस्टेंट होता है. टेम्परेचर चेंज करने से के चेंज होगा. टेम्परेचर बढ़ाने से के बढ़ेगा. रेट बढ़ेगा. मेरे को लग रहा है ये बात सबको समझ में आ रहा है. You all happy with this? Can I remove this clutter? Now this was the mathematical proof or an equation which will help you in solving all the numericals. Let me tell you what's exactly happening. And again, this is the beginning of something we'll do very often in times to come. We might want to plot the energy content of the system with the progress of the reaction, which is called the energy profile. This is called the energy profile. A process will start with reactants, end with products. This is going to be the energy profile. This is going to be the energy profile of a single step elementary process. So this is a fundamental energy profile of a single step elementary process, where a process starts with reactant, ends with products. You would shortly know the heat content at constant pressure is called enthalpy. So this is the enthalpy of the reactants, this is the enthalpy of the products. यहाँ पे एनर्जी अब्जॉर्ब हो रहा है, यहाँ पे एनर्जी अब्जॉर्ब हो रहा है. So this might very well be an endothermic reaction. पर एक एनर्जी प्रोफाइल में जो बिल्कुल टॉप वाला पॉइंट होता है ना, the peak of energy profile, the summit, this is called the point of activated complex. In another language, it's also called the transitory state. The summit point of the energy profile, it's called activated complex or the transitory state. यहां तक आने के लिए जो एनर्जी चाहिए होता है, इसी को बोलते हैं एक्टिवेशन एनर्जी. हर प्रोसेस का एक फिक्स मैकेनिज्म होता है. फिक्स मैकेनिज्म के हिसाब से फिक्स एनर्जी प्रोफाइल होता है. फिक्स एनर्जी प्रोफाइल की वजह से एक फिक्स एक्टिवेशन एनर्जी है. जो टोटल एनर्जी होता है, टोटल एनर्जी यहां तक का होता है, जो अगर तक का टोटल एनर्जी होता है उसको बोलते हैं थ्रेशोल्ड एनर्जी. Now suppose you are following this energy profile. Only till this point it's uphill. यहां तक आ गया, उसके बाद तो वो प्रोडक्ट बनेगा ही बनेगा. So how do you define activation energy? You define activation energy as the energy required to take part in the reaction or participate in the reaction. Reactant molecules का अपना कुछ एनर्जी होता है. The extra energy which they require. What is activation energy? Activation energy is the energy required by reactant molecules to take part in the reaction. यहां तक आ गया मतलब प्रोडक्ट बनेगा ही बनेगा. वहां तक आ गया मतलब प्रोडक्ट बनेगा ही बनेगा. Temperature is a measure of the energy content of these molecules. Temperature is a measure of the energy content of the molecules. In gaseous state, we actually saw it was directly proportional. The kinetic energy of molecules was directly proportional. You know, in thermochemistry, thermodynamics, you learn the internal energy will also be proportional to temperature. Temperature is a measure of the energy content of the system. टेम्परेचर बढ़ाओगे, टेम्परेचर बढ़ाओगे, टेम्परेचर बढ़ाओगे, more molecules will get activation energy, more molecules will take part in the process, and naturally all of this will translate into more rate of the process. Yes or no? So this is the mathematical expression. This is the mathematical expression which will help you in crunching numbers. And that I tell you is the graphical approach, which tells you about what is energy profile, what is activation energy, why is activation energy constant. And I think you're understanding me. This will find direct application. फिर प्रॉब्लम सॉल्विंग में डायरेक्ट एप्लीकेशन रहेगा, क्वेश्चन रहेगा, टेम्परेचर पे अलग अलग के का रेशियो निकालना रहेगा, टेम्परेचर कोएफिशिएंट निकालना रहेगा, ग्राफ में आपको क्वेश्चन आएगा. You will want to know it like anything. Log K2 by K1 is equal to E82 minus T1 upon 2.03 R T1 T2. Got me? ठीक है? अरे हाँ ना बोलो. I don't think I am going too fast for you, and naturally we'll revisit all of this in problem solving. But I need to tell you everything in one direction before I talk about reversibility. What happens in the textbooks and what happens in class 11, unfortunately, is they directly jump to the conclusion. So many of you would already know कि endothermic में temperature ज़्यादा रहना चाहिए, exothermic में temperature कम रहना चाहिए. You start following a rule called Le-Chatelier's principle. But trust me, in real life, in problem solving, that would take you nowhere. You'll want to start and understand it in the manner I'm telling you. So far so good, I believe. मेरे को लगता है यहाँ तक कोई कंफ्यूजन नहीं है. बच्चे लोग हाँ ना बोलो. बच्चे लोग हाँ ना बोलो. अब ना थोड़ा सा और अटेंशन स्पैन चाहिए मेरे को तुम लोगों का. अब मैं बात करने वाला हूँ रिवर्सिबिलिटी का. ये एक्टिवेशन एनर्जी हो रहा था रिएक्टेंट टू प्रोडक्ट. अब ये उल्टा आएगा प्रोडक्ट टू रिएक्टेंट. और अगर ये एक्टिवेशन एनर्जी था, अब मैं इसको बोलूंगा एक्टिवेशन एनर्जी फॉरवर्ड, और इसको बोलूंगा एक्टिवेशन एनर्जी बैकवर्ड. रिएक्टेंट से प्रोडक्ट भी हो सकता है, प्रोडक्ट से रिएक्टेंट भी हो सकता है. अब हम लोग रिवर्सिबिलिटी स्टार्ट करेंगे. यस और नो? अब हम लोग रिवर्सिबिलिटी का बात करेंगे. बच्चे लोग हाँ ना बोलो. पर पहले ये काइनेटिक्स समझना जरूरी है. पहले ये काइनेटिक्स, ये डायनामिक्स समझना जरूरी है. अगर तुमको ये समझ में आएगा, then only you will be able to relate to Kf by Kf1 is equal to EAF Kb2 by Kb1 and EAB T2 minus T1 upon 2.303 R T1 T2. Naturally, when you talk about reversibility, you're talking about Rf equal to Rb with temperature. Kf will change, which will change Rf. Kb will change, which will change Kb. And now we have to see how it affects the equilibrium. Yes or no? When Rf was equal to Rb, Kc was equal to Kf by Kb. Yes or no? अरे हाँ ना बोलो. When Rf was equal to Rb, the two reactions were having at the same rate and equilibrium was established. अब हम लोग देखेंगे equilibrium को कैसे affect करेगा. Now can I say now Kc1 will be equal to Kf1 by Kb1 and Kc2 will be equal to Kf2 by Kb2. Now I'm talking about Ks changing from Kf1 to Kf2, from temperature T1 to T2, and Kb changing from Kb1 to Kb2, from temperature T1 to T2. So if Kf would become Kf2 and Kfb would become Kb2, naturally Kc1 will become Kc2. बोलो बच्चे लोग. और if I have to take Kc2 by Kc1, which is Kf2 by Kb2 upon Kf1 by Kb1, can I take it like Kf2 by Kf1 upon Kb2 by Kb1? आराम आराम से देखो, कोई हड़बड़ी नहीं है. Kc2 by Kc1, which is Kf2 by Kb1, Kf2 by Kb2 upon Kf1 by Kb1. It could be written as Kf2 by Kf1 upon Kb2 by Kb1. ये दोनों सेम है ना? What was the mother equation? Log K2 by K1 is equal to EA T2 minus T1 upon 2.303 R T1 T2. यही है ना? ठीक है. टेम्परेचर चेंज करने से के चेंज करता है, टेम्परेचर बढ़ाने से के बढ़ता है, टेम्परेचर बढ़ाने से के बढ़ता है. अब रिवर्सिबिलिटी में क्या है? फॉरवर्ड भी है, बैकवर्ड भी है. तो जो फॉरवर्ड भी है, बैकवर्ड भी है, फॉरवर्ड के लिए एक्टिवेशन एनर्जी अगर ये है ये एफ, तो बैकवर्ड के लिए एक्टिवेशन एनर्जी ये होगा ये भी. यस और नो? So how would Kf change? Kf would change like Kf2 by Kf1 is equal to EAF, and the same remaining, everything remaining the same. How would Kb change? Kb2 by Kb1 is K changing with temperature from temperature T1 to temperature T2. Yes or no? And the reason I have brought it into this form is I want to bring it to this form so that I can apply say equation 1 and equation 2. Now if I write it in this form, I'll be able to apply equation 1 and equation 2. बच्चे लोग हाँ ना बोलो.
हाँ सर.
And if I write 1 minus 2, if I write 1 minus 2, if I write 1 minus 2, then log A minus log B is log A by B, log A minus log B is log A by B. And log of this by this, log of this by this would be log of Kc2 by Kc1. And that would be EAF minus EAB, and the rest remaining constant. You move at your pace, we're in no hurry. And you'll want to relate to this story. And very deliberately start from K instead of Kc. Because Kc is about Kf by Kb. And you would initially want to know K and how K changes with temperature. And then how Kf and Kb changes with temperature. And then how Kc changes with temperature. Yes or no? So once you know about log Kc, K2 by K1 is EA T2 by T1 upon 2.03 or T1 T2. And now you put it into reversibility. Reversibility में क्या होगा? Kf Kb के लिए दो अलग अलग इक्वेशन लिखेंगे. Kf चेंज करेगा, Kb चेंज करेगा. Yes or no? तुम लोग ऐसा कुछ सुने हो? डेफिनेटली थोड़ा तो सुनी होगी, भले ही मैं थर्मोकेमिस्ट्री नहीं पढ़ा हूं. ये अगर HR है, ये अगर HP है. Ever heard of delta H is equal to HP minus HR? It's called the heat of the reaction, enthalpy of the reaction.
इसने स्कूल में पढ़ा।
हाँ, आदमी स्कूल में ही पढ़ता है यार, कोई आदमी पढ़ो। You got your mobile phone back? See, you're not used to carrying it now. बच्चे लोग, give me a confident yes or no. Heard of delta H is equal to Hp minus HR? Now, delta H in chemistry has to be changed in heat. And a change in chemistry is reactant becoming product. And the delta is always final minus reactant. So final is final minus initial. So final is product and initial is reactant. And delta H is equal to Hp minus HR is the heat exchange in the process. जहां पर रिएक्टेंट से प्रोडक्ट में जाते हैं, ये रिएक्टेंट का एनर्जी कंटेंट है, ये प्रोडक्ट का एनर्जी कंटेंट है। बच्चे लोग हाँ ना बोलो। अब मेरे को देख के बताओ, ये जो डेल्टा एच का वैल्यू, ये जो डेल्टा एच का वैल्यू है, which I'm supposed to be writing as Hp minus HR, can't I write this as EAF minus EAB as well? I can write this delta H, I can write this delta H as Hp minus HR, and I can also write this as EAF minus EAB. तुमको ना क्लास 11 में इक्विलिब्रियम में डायरेक्टली ये इक्वेशन सिखाया जाता है। क्लास 11 में तुमको डायरेक्टली ये इक्वेशन सिखाया जाता है, बट इट्स वेरी इंपॉर्टेंट नॉट ओनली फ्रॉम प्रॉब्लम सॉल्विंग एस्पेक्ट बट इवन कंसेप्चुअली you got to understand, and trust me, this is very basic mathematics. You see it a couple of times, and trust me, the story which I am going to narrate along, you have a doubt, you can always fall back upon me. You have a doubt, and certainly the doubts would be diminishing with problem solving. This is theory only. So this is what you see in class 11. Log Kc2 by Kc1 is equal to delta H T2 minus T1 upon 2.C0 C R T1 T2. You're supposed to know delta H as Hp minus HR, and you're also supposed to know that in a reaction of this kind, where delta H is Hp minus HR or EAF minus EAB or positive, it's the case of an endothermic reaction. All of thermochemistry, all of thermodynamics will be told heat supplied is positive, heat liberated is negative. Heat supplied is positive, heat liberated is negative. बच्चे लोग, जल्दी से मैं तुम लोग को एक एक्सोथर्मिक का भी प्लॉट दिखा देता हूं। जल्दी से मैं तुम लोग को एक एक्सोथर्मिक का प्लॉट भी दिखा देता हूं। एंडोथर्मिक वाला बड़ा सा था, एक्सोथर्मिक वाला मैं छोटा सा दिखा देता हूं। अगर कभी भी ऐसे प्लॉट दिखे जहां पर HR is higher than Hp, naturally delta H, which is Hp minus HR, would be negative for a process which is exothermic, because Hp will be lower than HR. Common sense, अगर हीट लिबरेट हो रहा है, अगर हीट लिबरेट हो रहा है, अगर हीट लिबरेट हो रहा है, इट्स गोइंग टू अ लोअर एनर्जी स्टेट, यस और नो? अगर हीट लिबरेट हो रहा है, इट्स गोइंग इनटू लोअर एनर्जी स्टेट, यस और नो? So this will be the plot of an endothermic reaction. This will be the plot of an exothermic reaction. Exothermic में Hp is going to be less than HR. Do you understand? In exothermic, a very prominent fact would be EAF would be less than EAB. पहले धीरे-धीरे assimilate कर लो. That EAF minus EAB is the same as delta H. When EAF is more than EAB, एक तो difference is the same, even the sign is the same. When EAF is more than EAB, EAF minus EAB will be positive, and Hp is more than HR, so delta H is also positive. Yes or no? Endothermic में EAF is more than EAB. Exothermic में EAF is less than EAB. Are you all at peace with these results? Huh? People online will want to respond with a yes or no.
Yes.
दुखी नहीं होने का यार, बहुत आसान चीज है। अगला 15 मिनट में सब खत्म हो जाएगा। अगला दिन क्वेश्चन कुछ कराऊंगा इसका। प्रेशर, वॉल्यूम, डिग्री ऑफ डिसोसिएशन, डिसैक्रेट प्रिंसिपल, सब आसान आसान चीज है। अभी जो पढ़ा रहा हूँ ना ये भी आसान है, पर थोड़ा मजेदार चीज है, कंसेप्चुअल चीज है, ध्यान से सुन लो। तुमको सीधा ये बताया जाता है that Kc2 by Kc1 is equal to delta H T2 minus T1 upon 2.30 CR T1 T2. So this is pretty much keeping your requirement in mind. In class 11, you are told in endothermic, delta H is positive. So if T2 is more than T1, if T2 is more than T1, all of this will be positive. Endothermic में delta H is positive. If T2 is more than T1, all of this will be positive, and all of this will positive will mean Kc2 is more than Kc1. ये ना के था रेट, और ये जो केसी है ना ये है यील्ड। काइनेटिक्स इज अबाउट रेट, इक्विलिब्रियम इज अबाउट यील्ड। के बढ़ता है तो रेट बढ़ता है, केसी बढ़ता है तो यील्ड बढ़ता है, बिकॉज केसी क्या है? प्रोडक्ट बाय रिएक्टेंस। केसी क्या है? प्रोडक्ट बाय रिएक्टेंस। केसी क्या है? केसी इज सी टू द पावर सी डी टू द पावर डी अपॉन ए टू द पावर ए बी टू द पावर बी इन अ बैलेंस्ड इक्वेशन। ए प्लस बी फॉर्मिंग सी प्लस डी। केसी जितना ज्यादा होगा उतना प्रोडक्ट का यील्ड ज्यादा होगा। तो एंडोथर्मिक में टेम्परेचर बढ़ाने से रेट भी बढ़ता है, यील्ड भी बढ़ता है, रेट भी बढ़ता है, यील्ड भी बढ़ता है। एंड यू आर टोल्ड कि एक्सोथर्मिक में बिकॉज डेल्टा एच इज नेगेटिव, आई थिंक ये वाला पोर्शन सबको समझ में आ गया। एंडोथर्मिक में डेल्टा एच पॉजिटिव है, T2 more than T1, all of this is positive, log A by B positive would mean A is more than B। एक्सोथर्मिक में डेल्टा एच नेगेटिव है, तो यहां पर अगर T2 is more than T1, if T2 is more than T1, then negative positive will become negative, and Kc1 would be more than Kc2, or rather Kc2 would be less than Kc1। यही पढ़ते हो ना घूम फिर के कि एंडोथर्मिक में टेम्परेचर ज्यादा रखो, एक्सोथर्मिक में टेम्परेचर कम रखो। एक्सोथर्मिक में टेम्परेचर क्यों कम रखते हैं? क्योंकि मैथमेटिकली अगर T2 को T1 से कम रखते हैं, अगर T2 को T1 से कम रखते हैं तो ये भी नेगेटिव, ये भी नेगेटिव, और दो नेगेटिव पॉजिटिव हो जाएगा। तो Kc2 should be more than Kc1। एंडोथर्मिक में टेम्परेचर बढ़ाने का, एंडोथर्मिक में टेम्परेचर घटाने का। बट व्हाट इज द क्रक्स, और व्हाट इज द साइंस बिहाइंड इट? टेम्परेचर कैन नेवर हर्ट अ प्रोसेस। टेम्परेचर कभी किसी प्रोसेस का दुश्मन नहीं होता। टेम्परेचर कभी कोई प्रोसेस का दुश्मन नहीं होता। टेम्परेचर हमेशा, टेम्परेचर वुड इंक्रीज एनर्जी कंटेंट ऑफ द मॉलिक्यूल्स, it will get the molecules more animated, more excited, more vigorous. So before I end up going into the conceptual part of it, you'll want to very calmly focus and tell me if these numbers, or this negative, positive, and eventually exothermic low temperature favored is understood or not. And then I take you to the next and the final lab for the time being. यहां तक कोई प्रॉब्लम है तो बोलो। Delta H is Hp minus Hr, which is the same as EAF minus EAB, which is positive, and EAF is more than EAB for endothermic. and delta H is HP minus HR, which is negative, and EAF is less than EAB for exothermic. Yes, जो प्रोडक्ट्स है वो उसका नंबर बढ़ जाए. Yes. एक्सोथर्मिक में टेम्परेचर बढ़ाने से हीट कमता है, पर ऐसा क्यों होता है? और एनर्जी देंगे तो उस साइड का इक्विलिब्रियम डिसबैलेंस हो जाएगा, तो दोनों को. ये तुम जो बोल रहे हो मैं तुमको बताऊं, ये तुम बोल रहे हो ना, ये तुमको ली चैटलिस्ट प्रिंसिपल समझा दिया गया, घोल पिला दिया गया है, तो तुम ली चैटलिस्ट प्रिंसिपल के टर्म्स में बात करो. सही बात है. सर आप बोल रहे कि ये सब एनसीईआरटी में डायरेक्ट होता है, बताया. एनसीईआरटी का बात ना नाम ये है क्यों? के अंदर इसका बड़ा एक्सप्लेनेशन 5 पेज में सिर्फ लिखा हुआ है कि रिएक्शन इक्विलिब्रियम आने थे, रेट ऑफ फॉरवर्ड रिएक्शन और बैकवर्ड रिएक्शन सिमिलर. तो सबको गोली मारो. अभी मैं जो पढ़ा रहा हूँ समझ में आ रहा है कि नहीं? जल्दी बोलो, कम टू द पॉइंट. ये तुमको बता दिया गया है अभी तक कि एंडोथर्मिक में टेम्परेचर ज्यादा रखने का, एक्सोथर्मिक में टेम्परेचर कम रखने का, वो मैं भी बता दिया. एंडोथर्मिक में टेम्परेचर ज्यादा रखोगे, T2 मोर देन T1, एवरीथिंग इज पॉजिटिव, Kc2 इज मोर देन Kc1. Exothermic में to keep Kc2 more than Kc1, you want T2 to be less than T1, so the two negatives become positive. Yes or no? What's happening is the following. और मैं जब जेई मीन्स में क्वेश्चन कराऊंगा, कोई एंट्रेंस एग्जाम में क्वेश्चन कराऊंगा, तो अब मैं जो बताने जा रहा हूं वो ज्यादा काम आएगा. People online would want to respond with a yes or no.
Yes, sir.
So once in a while, I need this to be assured that you are awake and alert to the situation. Please hear me out. If there are two reactions, they'll have different activation energy. Yes or no? दो रिएक्शन का एक्टिवेशन एनर्जी अलग अलग होगा. For the same change of temperature, 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 क्या सब रिएक्शन का सेम रेट बढ़ता है? नहीं बढ़ता है. From same T1 to T2, from same T1 to T2, you'll have K2 versus K1 more if activation energy is more. Can I say this? सभी तो सबका टेम्परेचर कोएफिशिएंट अलग अलग रहता है. टेम्परेचर बढ़ाने से रेट बढ़ता है, टेम्परेचर बढ़ाने से रेट बढ़ता है, टेम्परेचर बढ़ाने से रेट कांस्टेंट बढ़ता है तो रेट बढ़ता है. कैन आई से जिस रिएक्शन का एक्टिवेशन एनर्जी ज्यादा होगा, जिस रिएक्शन का एक्टिवेशन एनर्जी ज्यादा होगा, फॉर द सेम चेंज ऑफ टेम्परेचर उसका रेट ज्यादा बढ़ेगा. ठीक है. दो अलग अलग रिएक्शन का, तीन अलग अलग रिएक्शन का, 10 अलग अलग रिएक्शन का रेट सेम चेंज ऑफ टेम्परेचर से कैसे चेंज होगा? प्रोपोर्शनल टू द एक्टिवेशन एनर्जी. A reaction having higher activation energy, a reaction having higher activation energy, a reaction having higher activation energy will have a higher change in K and a higher change in rate for the same change in temperature. Yes or no? You might want to write it down. You might want to write it down. A reaction having higher activation energy, a reaction having higher activation energy. मैं भी तुम्हारे साथ में लिखता हूं. A reaction having higher activation energy will have higher change in rate or rate constant for the same change of temperature. I think you're understanding me. Hello. हाँ निकुल. हाँ, क्लास में फोन करता हूँ। You all happy with this? अब देखो एक सिंपल सा बात है, टेम्परेचर बढ़ाने से हमेशा रेट बढ़ता है, टेम्परेचर बढ़ाने से हमेशा रेट बढ़ता है। एक्चुअली क्या होता है ये लिख लिया, टेम्परेचर बढ़ाने से हमेशा रेट बढ़ता है, जिसका एक्टिवेशन एनर्जी ज्यादा होता है उसका रेट ज्यादा बढ़ता है, जिसका एक्टिवेशन एनर्जी ज्यादा होता है उसका रेट ज्यादा बढ़ता है। ये सुनो, मैं बताया ना एंडोथर्मिक में ईएफ इज मोर देन ईएबी, मैं बताया ना एंडोथर्मिक में ईएफ इज मोर देन ईएबी। हाँ, I mean, I don't mind drawing a plot again, and in endothermic, I make you see that EAF is more than EAB. That's again the reason delta H is positive and all. So endothermic में क्या होगा, endothermic में क्या होगा, endothermic में क्या होगा? Because EAF is more than EAB, because EAF is more than EAB, because EAF is more than EAB, बोल मेरा बच्चा। ठीक है बेटा, मैं पढ़ा रहा हूँ अभी, मैं फिर कॉल करूंगा थोड़ी देर में, मैं क्लास में भी हूँ, मेरे को भी आधा घंटा 1 घंटा कोई फोन मत करना, ठीक है? हाँ, लॉलीपॉप भी लिखा हुआ है। The point is, I mean, I want you people to understand it inside out, not because there is a Le Chatelier's principle or these numbers, these formulas are telling you everything. Please hear me out. Endothermic में EF is more than EAB, टेम्परेचर बढ़ाते हो तो KF भी बढ़ता है, KB भी बढ़ता है, बट KF ज्यादा बढ़ता है, KF ज्यादा बढ़ता है बिकॉज दो अलग अलग रिएक्शन की क्या जरूरत होती है, फॉरवर्ड बैकवर्ड में बात करेंगे, यस और नो? टेक योर टाइम बट अंडरस्टैंड इट कंप्लीटली। एंडोथर्मिक में EAF इज मोर देन EAB, KF भी बढ़ता है, KB भी बढ़ता है, KF ज्यादा बढ़ता है तो नया इक्विलिब्रियम राइट में शिफ्ट हो जाता है, यस और नो? डू अंडरस्टैंड दिस? Because you believe that the one having higher activation energy will have the same change of, देखो फॉरवर्ड बैकवर्ड की तो सेम ही होगा चेंज टेम्परेचर ना। तो एंडोथर्मिक में EF इज मोर देन EAB, EF इज मोर देन EAB, तो टेम्परेचर बढ़ाने से KF भी बढ़ता है, KB भी बढ़ता है, KF KB से ज्यादा बढ़ता है, रेट भी बढ़ता है, और रेट फॉरवर्ड रेट बैकवर्ड से ज्यादा बढ़ता है, तो इक्विलिब्रियम राइट पे शिफ्ट हो जाता है, यस और नो? इसी को मैं अगर थोड़ा सा घुमा के लिख दूं, इसी को अगर मैं थोड़ा सा घुमा के लिख दूं, तो ये तो क्या KC2 is more than KC1, yes or no? Yes or no? I'm arriving at KC2 more than KC1, I'm arriving at KC2 more than KC1, not using this equation but using basic common sense, yes or no? What goes wrong in exothermic? Exothermic में ना टेम्परेचर कभी प्रोसेस का दुश्मन नहीं होता है। एक्सोथर्मिक में क्या होता है, एक्सोथर्मिक में क्या होता है, मैं एक बार प्लॉट भी यहाँ पर बना देता हूँ, मैं दो अलग अलग प्लॉट बनाता हूँ, हालांकि एक ग्राफ में समझ में आ जाता है एक प्रोसेस अगर आगे एंडोथर्मिक होता है तो पीछे एक्सोथर्मिक होता है, कि यहाँ पर EAF इज लेस देन EAB, यहाँ पर EAF कम है, EAB ज्यादा है, and because EAF is less than EAB, because EAF is less than EAB, KF2 by KF1 is less than KB2 by KB1, मतलब रेट बढ़ता है, टेम्परेचर बढ़ाने से रेट बढ़ता है, टेम्परेचर बढ़ाने से रेट बढ़ता है, रेट फॉरवर्ड भी बढ़ता है, रेट बैकवर्ड भी बढ़ता है, पर बैकवर्ड का रेट ज्यादा बढ़ता है, बैकवर्ड का रेट ज्यादा बढ़ता है। एंड बिकॉज बैकवर्ड का रेट ज्यादा बढ़ता है, बिकॉज बैकवर्ड का रेट ज्यादा बढ़ता है, यू नो अगेन क्रॉस मल्टीप्लिकेशन इन दिस inequality and you get Kc2 is less than Kc1. Yield decreases, yield कमता है, yield कमता है, लेकिन रेट बढ़ता है। टेम्परेचर बढ़ाने से, टेम्परेचर बढ़ाने से एक्सोथर्मिक में yield कमता है, पर रेट बढ़ता ही है, टेम्परेचर कभी रेट नहीं कमाता है। एक्सोथर्मिक में क्या होता है, टेम्परेचर बढ़ाने से फॉरवर्ड का भी रेट बढ़ता है, बैकवर्ड का भी रेट बढ़ता है, बट बैकवर्ड का रेट ज्यादा बढ़ता है, इसीलिए इक्विलिब्रियम पीछे आ जाता है, फिर हाँ नहीं बोलते हो। तो हम लोग क्या करते हैं, हम लोग क्या करते हैं, हम लोग क्या करते हैं, हम लोग यहाँ पे टेम्परेचर को कम करते हैं, हम लोग यहाँ पे टेम्परेचर को कम करते हैं। टेम्परेचर को जब कम करते हैं तो फॉरवर्ड भी घटता है, बैकवर्ड भी घटता है, बट अगेन बैकवर्ड ज्यादा घटता है, बैकवर्ड ज्यादा घटता है। जैसे टेम्परेचर बढ़ाने से फॉरवर्ड ज्यादा बढ़ता है, यहाँ पर टेम्परेचर घटाने से बैकवर्ड ज्यादा घटता है, yes or no? And because Kb decreases more than Kf, Kb decreases more than Kf, like Kb was increasing more than Kf, टेम्परेचर बढ़ाने से, टेम्परेचर बढ़ाने से रेट बढ़ रहा था, यील्ड कम हो रहा था, और यील्ड बढ़ाने के लिए जब टेम्परेचर कम करेंगे, एक्चुअली क्या हो रहा है, फॉरवर्ड का भी रेट कम हो रहा है, बैकवर्ड का भी रेट कम हो रहा है, और बिकॉज बैकवर्ड का रेट ज्यादा कम हो रहा है, बैकवर्ड का रेट ज्यादा कम हो रहा है, अपरेंटली इक्विलिब्रियम आ जा रहा है, यील्ड बढ़ता है, यील्ड बढ़ता है, बट रेट घटता है। इसीलिए एक्सोथर्मिक रिएक्शन में, इसीलिए एक्सोथर्मिक रिएक्शन में एक कंसेप्ट है, मैं खत्म कहाँ किया हूँ, डिड आई से दैट go back home and see you next day? I would not simply believe in these mathematical expressions. I want to know it very fundamentally. टेम्परेचर बढ़ाने से हमेशा रेट बढ़ता है, टेम्परेचर बढ़ाने से हमेशा के बढ़ता है, यहाँ पर केएफ केबी से ज्यादा बढ़ता है, रेट भी बढ़ता है, रेट फॉरवर्ड ज्यादा बढ़ता है, तो रेट भी बढ़ता है, और रेट फॉरवर्ड ज्यादा बढ़ता है तो इक्विलिब्रियम आगे चला जाता है। एक्सोथर्मिक में ना टेम्परेचर बढ़ाने से रेट नहीं कमता है, रेट बढ़ता ही है, बट बैकवर्ड का रेट फॉरवर्ड से ज्यादा बढ़ जाता है, तो बिकॉज बैकवर्ड का रेट फॉरवर्ड ज्यादा बढ़ जाता है, इक्विलिब्रियम पीछे आ जाता है। ठीक है, तुमको बोला जाता है टेम्परेचर कम रखो, टेम्परेचर कम रखो, तो टेम्परेचर कम करने से क्या होता है, फॉरवर्ड का भी रेट कमता है, बैकवर्ड का भी रेट कमता है, बैकवर्ड का रेट ज्यादा कमता है, इसलिए लगता है यील्ड बढ़ गया, एक्चुअली यील्ड बढ़ जाता है, इक्विलिब्रियम राइट पे शिफ्ट हो जाता है, बट यील्ड बढ़ता है लेकिन रेट घटता है, यील्ड बढ़ता है लेकिन रेट घटता है। इसीलिए एक्सोथर्मिक केमिस्ट्री में, एक्सोथर्मिक रिएक्शंस में देयर इज दिस कंसेप्ट ऑफ ऑप्टिमम टेम्परेचर। कभी सुने ऑप्टिमम टेम्परेचर? ऑप्टिमम टेम्परेचर इज द टेम्परेचर व्हेन यू वांट टू डू इट एट अ टेम्परेचर जिससे रेट भी ठीक ठाक रहे और यील्ड भी ठीक ठाक रहे, बिकॉज एक्सोथर्मिक का नेचर ऐसा है, you can't help reversibility, you can't help the fact that endothermic and exothermic will have, or exothermic will have this particular rate energy profile, you can't help reversibility, you can't help in every exothermic process, EAB will be more than EAF, and increasing temperature would mean backward increase will be more than forward increase, and there will be a letdown in the yield. So you want to do it at a temperature, टेम्परेचर उतना भी कम नहीं कर सकते ना कि यील्ड बढ़ाने के लिए रेट बहुत कम हो जाए, प्रोसेस शुड नॉट बी वेरी स्लो एज वेल, So you want to do a balancing act, you want to do it at a temperature called optimum temperature, जहाँ पर rate और yield के बीच में you can strike a balance. Naturally, the understanding will be clearer. Naturally, the understanding will be clearer with problem solving. But this is one round of kinetics plus equilibrium equations plus the graph which I wanted to, be at your end. You'll want to go through it a few more times. I'll give you a set of questions. Surprisingly, there will be a lot of questions in class 12 also. Actually, there will be more questions in class 12, less in class 11. Class 11 will be all about, more small little things here and there. At the end of the day, if you're happy with the catalyst principle, एंडोथर्मिक में टेम्परेचर कम रखने का, एक्सोथर्मिक में टेम्परेचर एंडोथर्मिक में टेम्परेचर ज्यादा रखने का, कम रखने का एक्सोथर्मिक में, whatever suits you. But this is something which all of you would have wanted to know. I'll give you a break of 10 minutes, and after 10 minutes, we'll talk about catalyst. It's going to be a shorter discussion. After 10 minutes, we'll wound it up with how catalyst affects the rate and the yield of the process. We'll resume in 10 minutes. All right. I think I can remove this letter. So, you can enjoy these 10 minutes to the maximum. All right. Rest to the best of your abilities. And then, as I told you, we'll wind it up with catalyst and their effect on the rate and the yield of the process. So now we want to talk about how catalyst is going to affect the rate and yield of a process. Before everything, I might have asked this question in the past. Does a catalyst take part in the reaction or not? It takes part in the reaction. So I'm used to people denying it right away. That's the way, we are supposed to know catalyst before class 11. So catalyst takes part in the reaction. You would have seen a catalyst is going to facilitate the process. And what does it eventually do? What does it effectively do? How does it speed down up or slow down the process? What changes? So catalyst can change the path of the process, the mechanistic path of the process. A catalyst would change the mechanism. Naturally, it will change the activation energy. बच्चे लोग, please hear me out. A catalyst takes part in the reaction. It alters the mechanism of the process, and naturally, by the activation energy of the reaction. I can see a particular sound, coming from some particular source. Make sure that, whoever is the source, you want to mute yourself in that case. It alters the activation energy of the reaction. So if I go back to log K is equal to log A minus EA upon 2.303 RT without changing the temperature, if I change the mechanism and the activation energy of the process, naturally if EA becomes EA prime, K will become K prime. And now if I write 2 minus 1, which is log K prime minus log K prime by K, log A will get cancelled, would be EA minus EA prime. 2 minus 3 will be this is positive and this is negative, yes or no? Yes or no? And right away, if EA prime is less than EA, if EA prime is less than EA, all of this will be positive.
Yes, you are right.
And K prime would be more than K, and you'll call it a positive catalyst. By default, a catalyst is going to mean a positive catalyst only. Let me quickly draw the energy profile for any reaction exothermic or endothermic. Reactant by product. See, this is what is happening. Either you supply more energy for more molecules to cross the energy barrier. इसको हम लोग energy barrier बोलते हैं, activation energy barrier बोलते हैं. Or you'd want to lower the hill, you'll want to make the process easier. This is what a catalyst does. अगर ये EA prime था, ये अगर EA था, if this was EA, and if this is EA prime, both graphically and mathematically, you understand this is an easier path to follow. Now more molecules will cross this energy barrier, more molecules will cross this energy barrier, yes or no? कैटलिस्ट क्या करता है? कैटलिस्ट एक्टिवेशन एनर्जी चेंज करता है, मैकेनिज्म चेंज करता है फॉर गुड. इफ इट चेंजेस इट फॉर गुड means if EA prime is less than EA, if EA prime is less than EA, mathematically you see EA prime less than EA would mean all of this is positive and K prime is more than K. So K prime is more than K would mean catalyzed process is faster. कभी कभी किसी प्रोसेस को कंट्रोल करना पड़ता है, कभी कभी किसी प्रोसेस को यू नो वी वांट अ प्रोहिबिटिव फैक्टर. और अगर EA प्राइम EA से ज्यादा हो गया, maybe in a given reaction when K prime is less than K, we'll want to call it a negative catalyst. So this is the case of a positive catalyst, this is the case of a positive catalyst, and naturally if it makes it more challenging, negative catalyst. Yes or no? I think you're all there with me. People online will want to respond with a yes or no.
Yeah.
Yes, sir.
Simple as it looks, at the same temperature, a catalyst, it takes part in the reaction, it's regenerated. In the process, it changes the mechanism, it changes the activation energy, it changes the mechanistic pathway. If it's becoming an easier path, it's lower activation energy. K prime is more than K, the process gets accelerated. A catalyst, which is generally taken as a positive catalyst, will lower the activation energy. Just in case a process needs to be of the rate of the reaction, you want to, do it at a lower rate, you might want to use a catalyst which is called a negative catalyst. बच्चे लोग हाँ ना बोलो. It alters mechanism, it alters activation energy, it alters the rate. Does it affect the yield of the process? You would have known by now. You would have known by now. Equilibrium में पढ़ते हम लोग. Catalyst does not change the yield of the process. It has no yield change. It does not change the yield of the process. In equilibrium, we are told the catalyst changes the rate of the process, but no effect on the yield, no effect on the point of equilibrium, the point of equilibrium, the point of equilibrium को जल्दी करता है पर ज्यादा नहीं करता है. Because why? Why? No, I want a better answer. It's not proportional to EA, it's not proportional to EA prime. It's proportional to the change. ठीक है. अगर ये इसको सिंपल करता है, अगर इसको ये आसान करता है, तो रिवर्सिबिलिटी में क्या होगा? फॉरवर्ड टू बैकवर्ड, बैकवर्ड टू फॉरवर्ड. जितना फॉरवर्ड को हेल्प करता है उतना ही बैकवर्ड को हेल्प करता है. यस और नो? So k prime k की जगह, k prime k की जगह, if I write log kf prime by kf is equal to EAF minus EAF prime upon 2.303 RT and log of kb prime e prime upon 2.303 RT. Don't you think these two are equal? Yes or no? What was the mother equation? The mother equation for a catalyst was log of k prime by k, log of k prime by k is equal to EA minus EA prime upon 2.303 RT. If you apply it for forward and backward reaction and see the corresponding change in rate for forward and backward, log kf prime by kf, log kb prime by kb. Now kf prime and kb prime by kf by kb, this would remain the same because the value is changing for forward and backward to the same amount. EF minus EF prime will be the same as EAB minus EAB prime. Yes or no? जितना forward के लिए आसान. बच्चे लोग हाँ ना बोलो. Now that naturally this will mean kf prime by kb prime would be the same as kf by kb, which in other words would be kc prime would be the same as kc. So there will be no change in the point of equilibrium. The point of equilibrium is not affected. Unaffected. Yes or no? कैटलिस्ट से सिर्फ यील्ड चेंज होता है, कैटलिस्ट से सिर्फ रेट चेंज होता है, यील्ड चेंज नहीं होता है. रेट नेचुरली फास्ट हो जाएगा. पॉजिटिव कैटलिस्ट हम लोग बोलते हैं बाय डिफॉल्ट. फॉरवर्ड का भी रेट बढ़ेगा, बैकवर्ड का भी रेट बढ़ेगा, दोनों का रेट बराबर बढ़ेगा, दोनों का रेट बराबर बढ़ेगा तो इक्विलिब्रियम चेंज नहीं होगा. कैटलिस्ट सिर्फ रेट बढ़ाता है, यील्ड नहीं बढ़ाता है. कैटलिस्ट से इक्विलिब्रियम जल्दी आ जाता है. It does not change the point of equilibrium. The equilibrium arrives earlier. Forward backward दोनों का रेट बढ़ा करके equilibrium जल्दी आ जाता है. You believe the reaction is happening quickly. So I think I'm being understood till this point. You'll want to take this information home. Certainly when we meet next, we'll explore factors like pressure, volume, concentration, Lee-Chatelier principle, which will be more routine things. I wanted you to go past this stuff which was more conceptual. I'm happy, we could complete this session today. Maybe I'll call you in a couple of days again, and then we'll do some routine stuff in chemical equilibrium, followed by problem solving. Go through this as many times as. Please come up with your doubts when you meet me next. Chances are the approach I have given you will be a foolproof solution to all questions which come in any interest with that. ठीक है बच्चे लोग, with your match I would have done it, I believe. Yes. So you'll find some questions in class 11, many questions in class 12. When we meet next, we'll take up small little stuff like degree of dissociation and TCKP and the relationship and all. So on this note, we'll want to conclude today. Stay happy, stay healthy, go through all of it, and come prepared with all of it in the next class. मिलते हैं बच्चे लोग. People attending online. See you soon. मिलते हैं. Bye bye.
Bye, sir.